Okay, so this video is going to finish off the discussion on the chemistry of conjugated dienes. So remember, we talked about the nature of conjugated dienes, why those are more stable than isolated dienes in a previous video. I also covered 1,2 versus 1,4 addition across conjugated diene. We talked about kinetic versus thermodynamic control, explained why you get, under what conditions you get kinetic, i.e. low temperature, versus thermodynamic, i.e. higher temperatures. Then I covered a little bit about UV-based spectroscopy, and then I covered Diels-Alder reaction and all its features. So this continues that discussion. So, okay. So 1 second, let me just make sure this is actually being recorded. Oh, I am recording. Forgot for a second. Okay, so I said when I started covering the Diels-Alder reaction that is one of 3 reactions that we classify as pericyclic reactions. So there are 3 of them. The first one is what we've already seen. That is the Diels-Alder reaction. So I'll just remind you, Diels-Alder reaction looks like this: diene reacting with dienophile. So the diene starts the process by pushing a pair of pi electrons, and then you get the flow of electrons as I'm showing here. And so I end up getting, in this case, a cyclohexene as my product. Now, a second type of pericyclic reaction is what we refer to as electrocyclic addition. So in an electrocyclic addition, this is the reaction that you're going to see occurring. So what's going to happen here is you're going to get this carbon take the pi of electrons, reach over, form a bond. So these pi electrons move over, and these pi electrons move over. So what you're going to get here, if you follow this, is you now have a double bond there, single bond there, a new bond form here, a single instead of a double at that position, and a single here. And then the third type of pericyclic reaction is what we call sigmatropic rearrangement. And you'll see we've already seen an example of this in Orgo 1. I'll remind you. So here, the reaction that occurs would be one like this, for example, where now what's going to happen is carbon takes the pi electrons and forms a new sigma bond there. Position of the double bond changes. I break this sigma bond and I form a new pi bond. So what I'm going to end up getting here is double bond here, single bond, single bond, single bond, and double bond, right? Remember when I was doing Diels-Alder, I said it's always a good idea for you to keep track of your carbons. That way you don't lose track of them. You don't suddenly have problems trying to come up with the product, or you don't suddenly lose carbons or add carbons. So I'll do the same here, and you can see where things end up. So this is 1, that's 2, 3, 4, 5, and 6. And if we go 1, 2, 3, 4, 5, and 6, then what I have is 1, 2, 3, 4, 5, and 6. Now, if you look at these 3 reactions, they share certain common themes that I'll just put on the side here. So I'll just refer to this as, let's say, common features that you see in all 3. First of all, if you really pay attention, you will notice that in all of them, the mechanism is concerted. And you already know what this means from Orgo 1. That means single step, there is no intermediate. Okay. A second feature that they share is that the mechanism in all three cases here involves a ring of electrons. So mechanism involves a ring of electrons moving around a closed loop. Third feature that I think you can distinguish here, in all three of them, is that the transition state is cyclic for all of these. So for example, in the case of the Diels-Alder, right, your transition state, remember, there is no intermediate, so I'm referring to transition state here. The transition state is as follows. I'll put it over here. So what's happening is you're starting to break that bond. You're starting to form that bond. You're starting to break that pi bond. You're starting to make that sigma bond. You're starting to break the pi bond here, and you're starting to form that sigma bond. Cyclic transition state. If you look at the electrocyclic, you are starting to form the double bond there. You're starting to break the pi bond there. You're starting to form a bond here. You're starting to break a pi bond here. You are starting to form a pi bond here. And you are starting to break the pi bond there, right? And the numbering would stay the same in that transition state. If I look at sigmatropic rearrangement, so beginning with 3 and 2, just as a point of reference, I'm starting to form a double bond there. I'm starting to break the double bond that was between 2 and 1. I am starting to form the bond between 1 and 6. I'm starting to break the pi bond between 6 and 5. I'm starting to form the pi bond between 4 and 5, and I am starting to break the sigma bond between 3 and 4. You look at all of them, and you clearly see that you have cyclic transition states, right? So I'll erase them just to clean this up, but I've just shown you that that is indeed something that is common to all three of them. And finally, a feature that they seem to share is number 4 here, is that solvent polarity generally has no effect on the rate of the reaction. So solvent polarity has generally, I'll put generally just so that we're qualify, we're clear about this. So solvent polarity generally has no effect. And of course, we mean on the kinetics of the reaction. The conclusion from this, of course, is that your transition state has little, and that's if any, so we're grudgingly saying maybe a little bit, but little, if any, charge. There is no charge. And indeed, you looked at the transition state of that just true. There was no charge that was actually involved. So we've already covered Diels-Alder in detail. Let's go into electrocyclic. So we're going to focus first on electrocyclic reactions. So the typical way this is shown in textbooks, and Klein does this, typical set of reactions we use to illustrate the major points we want to illustrate are as follows. If I were to start with the following specific molecule, right? And at the terminal positions, I have a methyl oriented like that and a methyl oriented like that. It turns out, if I go ahead and heat that, I end up getting the following product like that. So you know the reaction that's going to happen. I'll keep tabs here. 1, 2, 3, 4, 5, and 6. You can say 6 forms a bond with 1, pi bond moves over, pi bond moves over. So that means what I have is this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. The question, of course, becomes, and how do these two end up relative to each other on that six-membered ring, right? Do they end up cis to each other or trans to each other? So it turns out that when this reaction proceeds, the product that you end up getting, notice, is the cis version, where the two methyl groups are cis to each other. Now, if I take these reactions are reversible, so you notice I have an equilibrium set of reactions there. So we can go in either direction. So I could actually reverse this. Now, if I go ahead and I reverse this using heat, which is what I use to go forward, I'm going to get back the exact same thing that I started off with. But there's a curious little thing that was noticed. If instead of heat, I actually use light. And remember, whenever we, in chemistry, when we're saying a reaction is light driven, so it's photo controlled, we normally are just going to show Planck's constant and frequency to denote that it's light. So if I take this product that I have, the cis product, and I reverse it by heating, I get back the original. If I do it by light, however, what I end up getting is the following. And what happens here is that now notice where the two methyl groups end up, not the same way that they were oriented in the original molecule that I started off with. If I take this second product here and I treat it with light, I will get back the cis product. However, it turns out if I go ahead and this time I treat it with heat to reverse it, I'm going to get again the cyclohexene, but this time the two methyl groups end up trans to each other. And if I go ahead and I complete the cycle, I take this and I treat it with light this time, I will get the original one. If I treat it with heat, I get this one. If I treat it with light, I get the very first one that I had started off with. So you notice here that the orientation of the substituent, right, changes, and it seems to be changing depending on whether I am actually using heat or I'm using light, right? That's the important thing. Now, I can also do this using the following system. I'll put it on the side here where you see the similarity. So if I start off with this one now, so now 4 pi electrons instead of 6, which is what you had on the one on the left. Again, if I go ahead and I treat this with heat, right, what I'm going to get, if this is 1, 2, 3, 4, 4 reaches over, forms a bond with 1, and the pi electrons move over like that. So I end up forming cyclobutene. This is 1, that's 2, that's 3, and that's 4. And again, the question is, well, how do these two methyl groups end up relative to each other? Interestingly, here, what I end up getting is I end up getting the trans. So compare the result here when I heat that 6 electron system, and I hope you understand what we mean by 6. There are 3 pi bonds, 2 electrons for each pi bond, so that's a total of 6. You notice that you end up getting the cis product here. When I start with this one, which has the two methyl groups oriented the same way, out, so to speak, notice that when I treat it with heat, this time I end up getting the trans product. So that is actually different. So what happens to this if I do what I did to the other one? I now treat this with light. Well, the reverse is going to happen. And by the way, I didn't show this, but I think you understand here. The reverse would mean this goes back, this moves over, and this moves back, right? And so you notice I now end up with, in this case, I end up with one, 1 second. So what I end up with is, yeah, let me do it correctly. So what I do is I reverse here. So I end up, notice, with a double bond between 1 and 2. And 1 second here. Am I missing 1, 2? Sorry, I just realized, I think you guys noticed this. If I follow the movement here, I will end up with a bond between 1 and 6, a double bond between 2 and 3, and when I move this pair of electrons here, a double bond between 4 and 5, right? It was looking strange to me. And the same thing happens here. When, all right, so let me just continue there. So if I reverse what is happening here, I break that sigma bond between 1 and 6, move the pi electron, so I now have a double bond between 1 and 2. I have to move these pi electrons that way, so there's now a single bond between 2 and 3, but now there's a double bond between 3 and 4, and I have to move these pi electrons over to now form a double bond between 5 and 6. So that's what it is. So when I do the cyclization version here again, I do this, move this over, and move this over, you notice there's now a double bond between 2 and 3 and between 4 and 5. That's what I should have, and that's what I was looking straight. So when you reverse this one on the right, the 4 electron one with this, I will end up getting the acyclic product like that. And this time, what I am going to end up getting is, again, so notice the orientation of these two methyl groups is not the same as they are at the beginning here. And then, of course, what's going to happen if I take this and I treat it with heat, I'm going to cyclize again, right? And this time, what I'm going to get is going to be the cis. And if I take this and I now treat it with light, I'm going to get that. So again, what's important is to follow the orientation of the methyl groups we have there. And things are changing depending on whether I'm using light or I'm using heat. So I just wanted to show you this to really position the discussion that we are interested in. That clearly, whether I do the cyclization, right, which means like from here to here, or I do the ring breaking, as in from here to here, or I do cyclization again from here to here, or breaking that ring up to give me the open chain from here to here, and the same thing applies on the right. Notice that the results seem to be changing depending on the results, as in the stereochemistry of the two substituents on the ring, or how they're oriented in the open chain, clearly seems to be changing depending on whether I'm using light or heat. So how do we actually explain these results? And this is the critical thing that I want you to actually understand from all of this. This is explained by what are called the Woodward-Hoffman rules, right? So again, to emphasize here, we can explain this or these observations using what we now refer to as the Woodward-Hoffmann rules, which were established back in the by R.B. Woodward and Roald Hoffmann. So, what exactly do we mean by the Woodward-Hoffmann rules, and how do we actually use them to explain this? Well, I could show you, like Klein does, a little table or a little chart, and you would want to memorize if it's a 6-electron system, it must happen either with this rotatory or conrotatory, and then we will get cis or trans. If it is a 4-electron or an 8-electron system, do we proceed by this rotatory or conrotatory process? And do we get cis? Do we get trans? How many electrons are involved? And you can look up tables and try to memorize, or you can just understand it because it's not particularly complicated. So to understand this, we go back and we remind ourselves, all right, if we are talking about a 4-electron system, so this is the example that I used just now, here and here. So hopefully we agree. We have 2 and 2. What we have here is a 4-electron system, 4 pi electrons. So that means we have, notice, 4 carbons, right? I'll just quickly remind you, we have 4 carbon atoms. Each one is bringing 1 electron and its orbital, right? And these are going to try to combine. So what are the different ways in they can combine? So I'll remind you, best case scenario is that the waves match fully. And the way we show that, remember, is we say the amplitudes match. So shadeds all match. So that's going to give me a molecular orbital. I have the second most stable possibility, which is still lower in energy than the level here of my atomic orbitals, is where I have one node because these two waves match, but in between, I think you clearly see that you have a node, which means that is less stable than the lower one. So that's a molecular orbital. The third way in which these can actually combine is that these two in the middle are going to match, but there's a mismatch here and a mismatch there. So notice wherever you have a mismatch, that's where you have a node. So I have 2 nodes here, which is less stable than one node and the one below, which in turn is less stable than the lowest one, which has 0 nodes. And the worst case scenario for when these 4 orbitals from these 4 electrons from these carbons try to combine is that absolutely none of the waves match. So that doesn't match that, that doesn't match that, and that doesn't match that. And so what we end up with here is wherever there's a mismatch, like here, here, and here, there's a node. So I now have 3 nodes. So how many electrons do we have? We have 4 electrons. Each of these is bringing 1 electron to the process to try to have overlap of their orbitals. So when we fill 1, 2, 3, 4. So this represents the HOMO at the resting state, and this represents the LUMO orbital at the resting state. Now, if I have a 6-electron system, so if I have this one now, so again, to emphasize, we have 3 double bonds, 6 pi electrons. So again, we're going to have 6 carbon atoms, each with an electron, just like I showed for the 4. But to save time, what I'm going to just focus on is, well, how do the molecular orbitals actually look? So the best case, right, the lowest energy one is going to be where all 8 waves from these 8 orbitals from these, all 6 waves from these 6 orbitals, of these 6 carbons, they're going to all undergo constructive interference. So there's complete matching here, complete delocalization of the pi electrons. That's going to be one molecular orbital. The next higher in energy, so therefore a little bit less stable, is going to be one where I have one node. I have 0 nodes in the first one. So symmetry is always something we want to conserve. So that means the node will fall right in the middle. So where the node is, there's a mismatch between the orbitals on either side of that node. So what's happening, of course, is that right here you have the mismatch, and then these are actually matching. The next higher energy, therefore a little bit less stable than that one, is going to be where I have two nodes. And to maintain symmetry, I think you will agree, we would probably want to put a node here and a node there. That's where you're going to get the mismatch. So these two will match, these two orbitals will match, and these two will match, but you see where there's a mismatch. The fourth level, higher in energy, therefore less stable, is now going to have not two, but it's going to have three nodes. So for symmetry, these nodes are going to be here, here, and here. I think you can see the symmetry, which means this one doesn't match this one, but there they match here. There's no match here. There is a match here, and there's no match there, right? There isn't going to be a match. The two orbitals are on either side of my node. The fifth molecular orbital level, remember, if I start off with 6 atomic orbitals from 6 carbons, I have to get 6 molecular orbitals. In this case, what I'm going to have is, if I start with 0 nodes, 1 node, 2 nodes, 3 nodes, I will now have 4 nodes. So again, we always want to maintain symmetry. In fact, these are called the Woodward-Hoffmann rules of orbital symmetry in some textbooks. So what I'm going to have is a node right here. I will have a node right here. I will have a node right here and a node right there. And you see the symmetry, right? One side and the other side. So therefore, this one does not match this one, which doesn't match this one, but these two match. There's no node between them. There's no match here, and there is no match there. And then the worst case, the sixth one, is where absolutely nothing is going to match. And so now I'm going to have not 4, but 5 nodes, and those are going to be 1, 2, 3, 4, and 5. So therefore, there is no match between this one and this one. That second one does not match the third one, which doesn't match the fourth one, which doesn't match the fifth one, which doesn't match the sixth one. So I have 6 electrons. So when I fill 2, 4, and 6. So therefore, this represents the HOMO orbital, and this represents the LUMO orbital. And in fact, I'll do one more, and that's for what if we had an 8 electron system? Because you can conceivably see where the starting material would be this one. We have that, 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 and that. So you see 4 pi bonds. So let's say 1, 2, 3, 4, 5, 6, 7, and 8. So let's say I have methyl here and a methyl there. So 8 will form a sigma bond with 1. These electrons move over. These electrons move over. These electrons move over. Let's say I'm doing this with heat. So what I'm going to get is an 8 carbon ring. So what I'm going to have is that. So let's say this is 1, this is 2, this is 3, 4, 5, 6, 7, and 8. There's no a sigma bond that wasn't there between 8 and 1. There's a new double bond between 2 and 3, between 4 and 5, between 6 and 7, right? And then the question becomes, what is the stereochemistry of these two methyl groups? So I'm using a little wiggle line. Wiggle line in chemistry just means, okay, we're not saying whether it's cis or trans, we're just emphasizing the point. There will be some consideration about stereochemistry there. So I'm just showing you what the 8-electron system looks to now say, well, we can also construct, right? So we have 8 carbons involved, each one with a single electron. So you start off with 8 atomic orbitals. You have to end up with 8 molecular orbitals. So this is what they're going to be. Best case scenario, all 8 are going to match. Right? So that means shaded, matching shaded, 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 shaded. All of them are going to be shaded. The next higher one, as you would expect, would be one where you would have one node. And I think to maintain symmetry, you can quite clearly see that that means I'm going to have the node right in between. And so I have these 4 on the left that are shaded. There's now a mismatch here, and then there's a match between these 4. The next one is going to have 2 nodes. So the third one going up. So the nodes here are going to be right here and right there. So these two are going to match. This, this, this one, and this one will match. There's a mismatch here, and there is a match here. The fourth one will then have 3 nodes, right? So here, the nodes are going to be, one will be here, second one is going to be here, and the third one is going to be here, very symmetrical. So I have match here, then there's a mismatch, these two match, mismatch, these two match, mismatch, and these two match. Number 5 going up is now going to have 4 nodes. Right? So where are those 4 nodes going to be? One is going to be here. The second one is going to be here. The third one is going to be here. And the fourth one is going to be here, and you see symmetry. So this one does not match this one, but these match. There's a mismatch here, a match here, a mismatch there, a match there, a mismatch there. Number 6 is therefore going to be this one. So if I had 4 nodes in the previous one, this one is now going to have 5 nodes. Symmetry, remember, is important. One there, the second one there, the third one there, the fourth one there, the fifth one there. So this one does not match this one, which doesn't match that one, but here we have a match. Here we have a mismatch. Here we have a match. That is a mismatch, and that is a mismatch. So number 7 right? We have one more node. So this time the nodes are going to be 1 would be there, 2 would be here, 3 would be there, 4 would be there, 5 would be there, and 6 would be there. So you can see this one will not match this one, which doesn't match that one, which doesn't match that one. Here there is a match, there's a mismatch, a mismatch, a mismatch. And then, of course, the worst case is going to be this one, where absolutely nothing is going to match. And so I'll get 7 nodes. So this time, this one doesn't match that, doesn't match that, doesn't match this one, doesn't match that, mismatch here, mismatch there, and mismatch there. And so you can see I'm going to have 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes, 7 nodes. Again, each of these is a molecular orbital increasing in energy as I'm going up, which means getting less stable. I have 8 electrons, so 1, 2, 3, 4, 5, 6, 7, 8. So this is my HOMO in the ground state, and this is my LUMO in the ground state. Now, I will keep those and just each time come back and refer to them. So let's take a couple of cases and we'll see how we can explain this very readily. So for example, let's go to a four electron one. So we said that if I take this, all right, so you have this, so I'm just going to erase here, keep the orbitals, but just here so I have some space to go on. So if I say 1, 2, 3, 4, 4 and 1 form a bond, the pi bond moves over. And let's say that I'm doing this with heat, not light. We said that in that case, 1, 2, 3, 4, the methyls there end up being trans to one another. That's what we said. So how can we explain that they end up being trans? All right. When an electrocyclic reaction occurs using heat, then the HOMO that's going to be involved is the ground state one. It is what we're seeing there. Now, what it means, notice in this reaction, is that the electrons from the HOMO have to be pushed over so you can form that bond between carbons 4 and 1. Right? That's what starts things, and therefore we have to use the highest occupied molecular orbital, which is the HOMO. So notice that the HOMO here has 2 shaded up and it has 2 shaded down. So we could show this like that, right? So if we say 1, 2, 3, 4, so we can say at number 1, number 2, these are my 2 shaded up. At number 3, number 4, these are my 2 shaded down. Now notice how the methyls are. The methyls are oriented out, going away, out, going away. So therefore, at number 1, and I'll just take off the numbers that you see them there. That's just so that you could follow where I'm drawing these things. At number 1 now, that means my methyl group is going out, which means there's a hydrogen that is pointing in. There's a methyl out, and so there is a hydrogen that's pointing in, right? Or maybe I should show this hydrogen. Might be easier to show then the hydrogen is pointing in. Now, you notice that the sigma bond, the new sigma bond that is formed is this one between 4 and 1. It is a sigma bond, which means that you have to have head-to-head overlap. You cannot have side-to-side overlap. So what happens is that these orbitals at the end have to rotate. They have to swing or rotate in order to get either the 2 shaded or the 2 unshaded to match in a head-to-head fashion. We can actually simplify all of this by writing it this way. So if I take this and I swing it around this way, clockwise, then what we actually have, right? So I'll put numbers again so we keep track. That's 1, 2, 3, and 4. As I swing clockwise, I'm going to have 4 on that side and 1 on that side. So at 4, what I have is shaded up, shaded down, and shaded up. And when I swing clockwise, notice the methyl group will be here, the hydrogen will be there. That is connected to number 2. number 3, sorry. This is number 4. So that's number 3. Number 3 has the orbitals unshaded up, shaded down. 3 is connected to 2. 2, you notice, has shaded up and unshaded down. And 2 is connected to 1 here. Notice that 1 has shaded up, unshaded down, and when I swing over, the metal will be out and the hydrogen will be in. Take a moment and make sure that you are that you agree with me. Now, I'm going to turn on my camera for a second to emphasize the point. So I had the 4 carbon system like that, and I basically just swung it over like this, right? That's all I'm doing. I had it like pointing to the right. 1 and 4 would be here. And so my metal is that way, pointing that way. So when I swung over like that, the metal group is that way. So hopefully you can see that. That's what I wanted to emphasize. But we can actually simplify this even more because the orbitals at 1 and at 2 and 3 are not even participating in anything here. So we can basically ignore them. So we can take this that I've drawn and I'm going to simplify it for you over here. And I'll say that I'm only interested in number 4 and number 1. So number 4 here, number 1 here. Number 4 here, number 4, notice, has the methyl group that way, the hydrogen like that. Number 1 has the methyl group that way, the hydrogen like that. Number 4 is shaded down. Number 1 is shaded up. Now, for there to be a sigma bond, the 2 shaded or the 2 unshaded have to match. So I'm going to rotate the number 4 here clockwise. So let me go ahead and turn this on to say, this is what we're saying. The orbital is up and down, unshaded up, shaded down. The methyl is that way, the hydrogen is that way. I'm rotating counterclockwise like that, so that my unshaded, which is down, now pointing to the right. My unshaded that is down is now pointing to the right. My shaded, which is up, is now pointing to my left. So when I do that rotation, what I'm going to have here is the shaded one is on my right, the unshaded is on my left. But now, as I rotate clockwise, what happens to this methyl group as I'm rotating, counterclockwise like that? If it was this way, here is my orbital that I'm rotating. I am rotating the orbital counterclockwise like that. Notice this pen is representing where my methyl is. It's oriented that way to the left. The orbit, the unshaded is up, the shaded is down. So when I shade it to the right, notice the position of the methyl group. The methyl group ends up down. And let's not even bother showing the hydrogen. Now, I have to make sure the unshaded one at number 1 has to be pointing to the left so that it overlaps with the shaded one at number 1. To make that happen, I also have to rotate counterclockwise. That is now going to place the shaded to my left, the unshaded to my right. So now I have the shaded up, the methyl group is to my right. So when I rotate counterclockwise, notice where my methyl ends up. My methyl ends up, and then the rest of it is just connected via carbons 2 and 3. The key to this is, where do these end up? One ends up down, one ends up up. That is trans. If both had ended up up, that would be cis. If both had ended up pointing down, that would have been cis. But here, one is up, one is down, and that's trans. And that is exactly what we said the stereochemical outcome of this happens to be. right? Hopefully that makes sense. Now, what happens if, instead of doing this reaction using heat, I were to have used light? Here is the difference. Light does an important thing. Light will promote an electron from the HOMO up to what is currently the LUMO. In the higher energy state now, this one is no longer the LUMO. This one becomes the HOMO because that is the highest occupied molecular orbital. So now the orbital that we are going to use, molecular orbital that we're using to do the same analysis, is going to be that one which used to be LUMO, but it's now HOMO because one of the electrons has been promoted by light. Heat cannot do it, light does it. So light is going to cause that promotion. Now notice the difference. Focus on the terminal ones. This is shaded up, this is shaded up, which is different from the ground state HOMO, where that's shaded up and that's shaded down. So the difference in the analysis is now going to be that as I do this, the only thing that's going to change in my new HOMO is that the two end ones are both shaded up. One is shaded up, 4 is shaded up. So I'm going to take 4 here and I'm going to change this to represent that it is shaded up. And 1 here is also shaded up. So therefore, I go to the simplified version, which is this one, and I am going to also shade up. Nothing, absolutely nothing changes. One quick thing before I do this one. Notice that here I rotated counterclockwise and here I rotated counterclockwise. When I rotate both of them clockwise or both of them counterclockwise, we say that we've rotated in a conrotatory fashion. So that was conrotatory when we did it under heat. Now let's do this one. So I've changed this now to where I now have both of them shaded up. So again, we can choose to have the shaded ones or the unshaded ones match. Pick whichever one you want. I'll draw it up here, in fact, so that I have a little bit more space. So how do I make them match? Which one? I'll go ahead and make the unshaded ones match. So I'm going to rotate this one counterclockwise. That's right. So notice the metal is here. My shaded is up. So when I rotate counterclockwise, metal ends up down. When I rotate counterclockwise, that places the unshaded to my right, the shaded to my left, and importantly, the metal is down at carbon number 4. I need for my unshaded on carbon number 1 to now be to the right so that it matches. To do that, notice I will now rotate clockwise. When I rotate clockwise, here is my metal. Now the unshaded is at the bottom here. So if it's down here, I have to rotate this way, right, in order to put the unshaded to the right. And where does my metal end up? It ends up pointing down. So when I do that, the unshaded goes to the left, the shaded goes to the right, and my metal group ends up here. I connect that. Okay, this time, unlike before, the two metal groups are pointing down. That means that that is going to be cis. So if I do the same reaction, but I do this reaction using light, not heat, I'm going to get this, but I'm going to get these two being cis. When I use light, when I use heat, sorry, up here, I get the cis, the trans, sorry, but when I use heat, I get the trans up here. But when I use light, I get the cis down here. And that is really how you have to think of this in terms of the Woodward-Hoffman rules. Now, I rotated this one counterclockwise, and I rotated this one clockwise. So when I rotate them in the opposite, right? So remember, in the previous one, I rotated both of them counterclockwise and we said conrotatory. If I had rotated both of them clockwise, that's conrotatory. But if I'm rotating one counterclockwise and one clockwise, this is what we call this rotatory. So you see the difference. I have to rotate this rotatory in a 4-electron system when I'm doing it under light, and the result is cis. I have to rotate conrotatory in a 4-electron system when I am doing it with heat, and the results are trans. But keep in mind that that is when I had the two methyl groups, one pointing up and one pointing down. So now that we know how to simplify this, I'll just go ahead, erase this, make it cleaner, and show you what I mean by the initial orientation of the two methyl groups is also important. Let's say that I was actually starting off with this, but I had one that way and one that way. If I'm doing this under heat, I'm doing it under heat, this is the HOMO we're dealing with. The terminal ones, one is shaded up, one is shaded down. So I'm going to use the simplified version. So here I have shaded up, and on this side, I have shaded down. This time, one methyl group is pointing out, and one methyl group is pointing in, and then they're connected via carbons 2 and 3. So let me go ahead and match the unshaded ones. So I would rotate here, that is counterclockwise. That is going to put the unshaded on my right, the shaded on my left. And when I rotate counterclockwise, the methyl group will end up down. So to make sure that the unshaded one is to the right from the other one, I would actually have to rotate counterclockwise also. That places the unshaded on the left, the shaded on the right. And when I do that, the methyl group ends up down. And so therefore, I end up with the cis. And if I'm rotating counterclockwise here and counterclockwise here, that is, of course, conrotatory. Right? Now, what if I were doing this, but I'm not using heat, I'm using light? Then the LUMO becomes this one. In this one, notice the two terminal ones are shaded up. So the difference is going to be, I have to now show both of them being shaded up, right? Everything else remains the same. So therefore, when I rotate counterclockwise here, I place my shaded on the right, and my unshaded on the right, shaded on the left, the methyl group points down. To make the shaded one be to the left here, I have to rotate clockwise. But when I do that, notice the methyl group, which is here, now ends up. So this time, the methyl group here is going to end up that way. So I actually end up with a trans product. And if I rotate it counterclockwise here and clockwise here, that is, of course, this rotatory rotation. Make sense? Let's do the 6-electron system because it all is exactly the same. So you see, knowing this, you can work out anything really. You don't have to really memorize absolutely anything. So let's look at this one. So I'll draw it up here so that I work coming downward. So here I'm starting off with this, right? So that I can draw down here. Okay. If I'm doing this using heat, then the HOMO that I'm going to be using is the regular one. we're only interested in the terminal ones. And you notice that the two terminal ones are both shaded up. Therefore, I'm going to have shaded up here, and I'm going to have shaded up at the other one. So notice that the two methyl groups here are pointing outwards. So that means I have the methyl out, and then the rest of it is connected by carbons 2 through 5. If I want to have a match. So this time I'm going to make the shaded ones match, but it makes no difference. So I need for this one on the left for the shaded one to be on the right. So that means I'm going to rotate clockwise. When I rotate clockwise, that places the shaded one on the left, the unshaded one on the right, and my methyl group will end up pointing up. To make the shaded one be oriented to the left on the other carbon, I have to rotate counterclockwise. That'll place the shaded on the left to match, the unshaded on the right. And when I do that counterclockwise movement, that places the methyl group up, and the rest of it is just connected by the ring. So notice that I get a cis because the two methyl groups are pointing the same direction. And here I rotate clockwise on the left and counterclockwise on the right. So which type of rotation did I do? I did a this rotatory rotation. Now, what if I make one change? What if I do the same reaction, but instead of using heat, I use light? So light will make one of these electrons go up here, and this becomes my new HOMO. Focus on the terminal orbitals, shaded up, shaded down. So I have to change this. One is shaded up, therefore the other one is going to be shaded down, right? And therefore, right, I need to make them match. So I'll go ahead and if I rotate this one counterclockwise, that places the unshaded on my right and the shaded on the left. That movement will place the methyl down. So I have to rotate counterclockwise here in order to have the unshaded that way and the shaded this way so that the unshaded match. And in doing that, my methyl group will end up going up. Since the methyls, one is up, one is down, I will end up with the trans product. And if I rotate it counterclockwise in both cases, then I'm doing con-rotatory rotation. And you see this, right? Same thing that I would do here. If I am going ahead and I'll just change this one just so that it's different. Let's say that in this case, one is out and one is pointing in. So since I'm doing this with just heat, this is at the ground state, and that means I'm using this HOMO. Focus on the terminal ones, shaded up and shaded down. So what I have is one of them is shaded up, the other one is shaded down. One of them has the methyl pointing in, one has it pointing out. The rest of the molecule is connected by the other six atoms. So in order to match here, I'm going to rotate this one counterclockwise. That is therefore going to place the unshaded on my right and the shaded on my left. And that counterclockwise movement will place the methyl up. To make the unshaded match, I have to rotate here counterclockwise. That'll now have the unshaded to my left, the shaded to my right, and that counterclockwise rotation means that the methyl will end up. So therefore, since the two methyls end up pointing up, then I know that my product is going to be cis here. And since I'm rotating in both cases counterclockwise, that is doing a this rotatory. Now, if I were to instead do this reaction using light, one of these gets promoted, this is now my new HOMO. And therefore, notice the terminal positions, shaded up and shaded up. So I have to come here, change, so that both of them are now shaded up, right? And the two methyl groups are, right, in and out. So if I rotate counterclockwise, that places the um, unshaded pointing to my right, the shaded to my left, and it means the methyl group is up. To make the unshaded match, I have to rotate clockwise. When I do that, the methyl group is now down. So this time I will end up trans. And if I'm rotating counterclockwise on one and clockwise on the other, then I have done this rotatory rotation, right? That is what we want you then to actually get from electrocyclic reactions, that you know how to do. Oh, and by the way, one quick thing, working backwards is exactly the same. In other words, we know let's use a simpler one here, maybe. We know that what's happening here is you're getting here, here, and here. So the product that you get is going to be the six-membered ring, double bond, double bond. And we said that if you do it with light, let's say, that the product ends up being trans. So therefore, I have methyl and methyl trans to each other. I can reverse this process to go in that direction, right? It's the exact same thing. We would look at what we have. So this is what we actually have. For me to reverse back using light, I have to get back to this HOMO orbital, where you notice again the terminal position. One is shaded up, one is shaded down. So for example, here, what I would do in order to have one shaded up, one shaded down, I could break this one that way. So that would now put the shaded up and the unshaded down. And if I move clockwise, that's going to put the methyl like that. And in order to have the other one shaded down, because again, this is the orbital we have to get to, in order for the shaded to be down, I would have to move this one like that. That is going to put the unshaded up, the shaded down, and that movement is going to place my methyls like that. So if I were to be here and I treat this with light to go back, the two methyls will be pointing outwards. So in other words, I should get exactly this one, right? So it works in either direction. Okay. What about electrocyclic sigmatropic rearrangements? What do we need to know about sigmatropic rearrangement? Not much really. One major task that you have to know. Well, first of all, of course, the major task is to recognize when you've had a sigmatropic rearrangement. So here's your classic case of a sigmatropic rearrangement. So again, just to keep tabs, I will number here. We'll do a different kind of numbering in a second, which is important. So let's say that I have 1, 2, 3, 4, 5, 6. I'm going to warm this up. What will happen is 6 forms a bond with 1. The pi electrons move over. You break the 3 to 4 sigma bonds and form a new double bond between 4, and 5. So notice that I have broken that bond. So that means if I start with 3, 3 now has a double bond to 2. 2 now singly bonded to 1. There's now a sigma bond between 1 and 6 that wasn't there before. There's now a single bond between 6 and 5, and there is now a double bond between 5 and 4. So that's just for us to keep track of where things are, right? So that's the first thing, you have to be able to show what the product is. I'm going to remove these numbers because the important thing now, the biggest challenge we have for you in sigmatropic rearrangement is for you to tell us what type of sigmatropic rearrangement exactly did you have. And the way to do this is identify which is the bond, the sigma bond that you broke, and which is the sigma bond that you actually formed. So I broke that sigma bond, and I am forming a new bond here. So this is a new bond that was formed, and right here is where the bond used to be that I broke. So you see where I've highlighted in yellow. Starting at this end, count until you get to that end of the yellow. 1, 2, 3. Starting at this end, count how many atoms you have until you get to that end of the yellow. 1, 2, 3. So therefore, this is what we refer to as a 3-3 sigmatropic rearrangement. That's the biggest challenge. Which type of sigmatropic rearrangement you have? Here's another example of a reaction that falls under sigmatropic rearrangement classification. If I have this particular, again, I will put, in fact, let me put letters here instead of numbers, and then I'll erase them. So let's say A, B, C, D, E, and F. So F will grab the hydrogen, the proton, the sigma electrons forming the A to B move over to B and C, and the pi electrons move over here. Again, we would warm. So what I would end up getting is that if this is B, it no longer has the A atom, which is the hydrogen, but it now has a double bond to C. There's now a single bond to D. There's now a double bond to E, and this methyl group is still there. There's now a single bond to F, and F now has its bond to hydrogen. So which sigma bond was actually broken? Right here, the carbon to hydrogen. And which bond has been formed? It's this one, hydrogen to there. So I broke the beta hydrogen, which is A, and I now have formed a new sigma bond here to here. So this time I count from the end of this yellow to the end of that yellow. Well, there's only one. So let me erase the letters. That was just for us to keep tabs of where everything happens to be. Okay, so from this end of the yellow to that end of the yellow, it's like we went from this end to that end, there's only one atom. From this end to that end, we have 1, 2, 3, 4, and 5. So what I have here is a 1,5 sigmatropic rearrangement, right? Now, that really is the biggest thing that we are going to have. Now, this example here, let me show you a specific example, just slightly more complicated, and that's just because I'm going to introduce a methyl group here. So when this undergoes a sigmatropic rearrangement by warming, it's going to go this way, and that way. So if you follow that, what you will now have is a double bond here, single bond there, a new sigma bond there, a single bond there, and a double bond there, and my methyl group is here, right? So these are all equilibrium reactions, I should be saying. An interesting question here is which side is favored? So what you find here is that at equilibrium, you have 15% of this and 85% of that. So clearly, the forward direction is favored, so I should more accurately write it like that, because that forward direction is the one that is favored. So then, a question that you might ask is why? pause here and think for a minute or so, look at the structures, and you should know why the equilibrium is favored to the right. So pause here, come back, then see if you got it. All right, assuming you've come back, you've paused, you have two double bonds here. What's the degree of substitution? This double bond is mono-substituted. This double bond is mono-substituted. I look at my two double bonds here. This double bond is mono-substituted, but here's the difference. That double bond is di-substituted. So I go from having two mono-substituted to a mono and a di, and we know that a di-substituted alkene is more stable than a mono. So that's the reason, Seitzer's rule, why that actually happens. And this reaction here, right, where did I actually break a bond? So I broke this bond. And where did I form a sigma bond? This is the sigma bond that I formed. So therefore, when I count from this end of that little broken line to that end, that's 1, 2, 3. And when I count from this end to that end, that's 1, 2, 3. So what I have here is a 3-3 sigmatropic rearrangement. And this one is specifically called a Cope rearrangement. So there are quite a number of these sigmatropic rearrangements that actually have names. So that's the Cope. You can also have what's called the oxycope. You can have the Ireland, the Claisen Ireland, the Claisen as examples. So let me just illustrate with one that you already know. In Orgo 1, we talked about one reaction that some ethers undergo that we called the Claisen rearrangement. And we said that the Claisen rearrangement occurs when you have two specific types of ethers. When you have allyl vinyl ethers, or when you have allyl aryl ethers. So an allyl vinyl ether would be, so this position is vinylic and that position is allylic, so allyl vinyl ether. An allyl aryl would be something like this. Where that's an allylic position and that's an arylic position on an arene. We actually saw this when we talked about Claisen rearrangement back then. So let's say, for example, that I use this one to illustrate what's happening. So if I have that, all I'm going to do is change the orientation, how I draw the molecules slightly. So here, I'll put numbers 1, 2, 3, oxygen is 4, 5, and 6, just so that we keep track. 1, 2, 3, oxygen is 4, then you have 5, and then you have 6. If now 6 and 1 form a bond, pi electrons move over. You break the carbon 3 to oxygen bond and move those electrons here. So as I follow, I now have a single bond between 1 and 2. I now have a double bond between 2 and 3. I broke the 3 to 4 bond. There's a new bond between 1 and 6. There is a single bond between 6 and 5, but there's now a double bond between 5 and the oxygen, which is 4. What kind of a rearrangement would this actually be? Here is the bond, the sigma bond that I form. Here used to be the sigma bond that I break. So when I count from this end to that end, it's exactly what's there. 1, 2, 3. I'll take out these numbers. No, that was just for orientation. When I number from that end to that end, 1, 2, 3, notice that that is also an example of a 3-3 sigmatropic rearrangement, just that we didn't call it that at the time. So that's it for sigmatropic rearrangement. We just expect you to be able to know when a sigmatropic rearrangement is happening, to be able to predict what the product is going to be. And to tell if it's a 1,5, a 3,3, or whatever the case might actually be.